In order to calculate the electric field due to a discrete charge distribution, we can apply the relation of the superposition principle. According to this principle, the net electric field strength E at any point in the field of the charge distribution is equal to the vectorial sum of the electric fields due to the individual charges at that point. This method of finding the net electric field at a point becomes impractical in the case of continuous charge distributions, such as a linear charge distribution, a planar charge distribution, or a volume charge distribution. In this module, we discuss about a linear charge distribution. Let us now consider an infinitely long straight wire carrying a uniformly distributed positive charge. Its linear charge density, lambda, is the charge per unit length of the wire. That is, lambda is equal to Q by L, where Q is the total charge on the conductor distributed over length L of the wire. The wire considered has an axis of symmetry. Consider a point O on the wire. Consider a radial vector from O to a point P whose magnitude is R. This radial vector is normal to the length of the wire. If we rotate the radial vector about the point O, we get a circle. Several points on the circumference of the circle obtained are equidistant from O. Hence, the electric field due to the charge on the element of the wire at O is equal in magnitude at all the points on the circumference. The direction of the field at any point on the circle is always radially outward. The fact that the electric field strength at any point is directed radially outward can be understood by considering two small elements of the wire at equal distances from O on either sides of it, as shown. Let the element at the point above O be A, and the element at the point below O be B. Then, the field at P due to the element at A, EA, acts along AP. Similarly, the electric field at P due to the element at B, EB, acts along BP. As the two elements, A and B, are equidistant from O, they are also equidistant from P. Thus, the magnitudes of the electric field strengths due to A and B at P are equal. To get the net electric field strength at P due to A and B, we resolve these electric fields into horizontal and vertical components. EA is resolved along AC and AO, which are along the horizontal and vertical directions. Similarly, the components of EB are along BD and BO, which are also along the horizontal and vertical directions. As the magnitude of EA and EB are equal and elements A and B are symmetric about O, the magnitudes of the horizontal components of the electric fields are also equal. Similarly, the magnitudes of the vertical components of the electric fields are also equal. We observe that the directions of the vertical components of EA and EB are opposite. Hence, they cancel each other. The horizontal components are parallel to the radial vector along OP. Thus, the net electric field at P due to the elements at A and B is equal to the sum of their horizontal components and acts radially outward. This is true for any such pair of elements considered on either side of the element at O. Thus, the field at any point under consideration, like P, is radially outwards. As the length of the wire is infinite, the electric field strength does not depend on the position of the point under consideration, P, along the length of the wire. Thus, the electric field due to the wire of infinite length is radial everywhere and in the plane normal to the length of the wire. It depends only on the magnitude of the radial vector r. Now let us calculate the electric field strength due to the charged wire at a point which is radially at a distance r from the wire. In order to calculate the electric field strength due to the wire, let us consider a Gaussian cylinder of radius r around the wire. Let the length of the Gaussian cylinder be L. According to Gauss' law, net flux phi through a Gaussian surface is equal to Qin by epsilon naught, where Qin is the charge enclosed within the Gaussian surface. Let this be equation 1. We know that phi is equal to integral E dot dA, where E is the electric field strength. At all points on the Gaussian cylinder, the electric field strength E is perpendicular to the curved surface of the cylinder. Since the electric field due to the charged wire points away from the positively charged wire as discussed earlier. If we calculate the net flux phi through the Gaussian surface, the net flux through the surface will be the sum of electric flux phi 1, phi 2 and phi 3 through the surfaces 1, 2 and 3 respectively, as shown. Surfaces marked 1 and 2 are the circular surfaces of the Gaussian cylinder, and the surface marked 3 is the curved surface of the cylinder. Let us now calculate the electric flux through surface 1, which is the flat surface of the cylinder. We know that the electric flux phi 1 is equal to E dot A, where E is the electric field and A is the area vector. This is equal to EA cos theta, where theta is the angle between the directions of electric field and the area vector. The electric field is perpendicular to this surface. Hence, in this case, theta is 90 degrees and cos 90 degrees is equal to 0. Hence, flux phi 1 through this surface is 0. Similarly, we see that the electric field is also perpendicular to surface 2, and hence flux phi 2 through this surface is also 0. Hence, the total electric flux phi is equal to the electric flux phi 3 through surface 3, which is the curved surface of the Gaussian cylinder. Let the surface 3 be assumed to be divided into infinitesimally small elements, each of area dA. There will be a net electric flux through this surface. Since the electric field strength E for any point on the surface is parallel to the area vector dA for the element under consideration. Since E will be parallel to the vector dA, we have electric flux d phi 3 passing through the element equal to E dot dA, which will be equal to EdA cos 0, and this will then be just equal to EdA. Let this be equation 2. To find the total electric flux phi through the Gaussian surface 3 We now integrate d phi 3. Therefore, phi is equal to integral d phi 3, and this is equal to integral EdA. Since all points on the Gaussian surface 3 are equidistant from the charged wire, the magnitude of electric field strength E for any point on the Gaussian surface is a constant. Therefore, we can write phi is equal to E into integral dA. We know that integral dA is equal to A, which is the area of the Gaussian surface considered. Therefore, phi is equal to EA. The area A is equal to 2 pi RL, which is the curved surface area of the cylinder of length L and radius R. Substituting the value of A in the expression for total flux phi, we get phi equal to E into 2 pi RL. Let this be equation 3. From equations 1 and 3, we see that E 2 pi RL will be equal to Q by epsilon naught. Let this be equation 4. Here, Q is equal to the product of the linear charge density, lambda, and the length of the Gaussian cylinder, L. Substituting the value of Q in equation 4 and simplifying, we get E equal to lambda by 2 pi R epsilon naught. Let this be equation 5. Vectorially, E is expressed as lambda by 2 pi epsilon naught into n cap, where n cap is the radial unit vector in the plane normal to the wire. Vector n cap will point away from the wire if lambda is positive, and it will point towards the wire if lambda is negative. From expression 5, we see that the electric field strength E, due to an infinite long straight wire, is independent of the L value. Therefore, the field strength is constant in both magnitude and in direction, thus representing a uniform electric field.